So, first speaker. That's not worrying at all. I was a little bit stressed out this morning about doing this, being the first speaker on in front of all of you guys, because I don't particularly do so well when it comes to public speaking. So I rang my daughter, had a video call with her, and said, Esme, I'm really, really nervous. What do I do? And she said, Daddy, be quiet, Peppa Pig is on. So, you know, just that's the useful advice from my 3-year-old. So, for those of you that know me, hello. Look forward to catching up with you. For those of you that don't know me, my name's Chris Knight. I work for Beckhoff Automation in our UK branch. I've been there for 10 years now. I originally started off just working on support and branched out into MATLAB support, LabVIEW support, C++, and a few other languages as our business grew over in the UK. One of the things that I wanted to cover off in this presentation today is to look at how we have solved, or how we solve with some of our customers, the issue of controlling quite large-scale systems that require you to use integrated measurements and motion, safety, and so on. So I have a very stripped-back presentation where we can have a look through and see some of these things in action. Obviously, a lot of these projects were done in NDA, so this is just a general overview of what topics came up in that. So, our project that we're going to look at is quite a complex one. This was actually a real project that we did. It required us to do really complex measurement applications, so really high precision measurement. We also needed to actually control some stages for some experiments, so we actually needed full motion. We needed that to be synchronized as well, because the measurements we were taking happened under different conditions, and the drives were used to orient the experiments and so on in time for those tests. We also had to have safety integrated, and one of the big things about all of this was that this had to be done over distance. Yeah? Some of the runs between these individual stations that we had were up to 100 meters. Yeah? Some could have been longer, but we basically ended up with some networks, or networks in total, that were in the kilometers in total distance. Okay? So that was our starting point. We needed, because of the customer, to end up with LabVIEW at the top end, hence the relevance here. And essentially what we needed to do was gather all this data together in one place and bring it all back to LabVIEW. Okay? So our requirements were some form of PC, running some real-time control for our drives and motors. We needed to have multiple cycle rates. There was lots of different things going on at different speeds within the machine itself. And we needed to have some powerful CPU to do the LabVIEW processing. We had some intense analytics going on. And it also needed to be able to support multiple networks. Okay. We needed SIL3 PLE safety, which isn't particularly easy to achieve in these systems, and it needed to be distributed. We had lots of places where workmen and engineers and stuff could go in and out of the experimental rooms, and I needed to be able to then control those independently. For the experiments, we needed some point-to-point motion, but we needed to synchronize quite a bit of it as well, so that actually all these things rotated in exact precision, synchronous with each other. And we needed to actually run external set points. Some of the experiments, the customer actually had a set of known positions they wanted the system to go through, didn't want to bother programming it with standard sort of motion control systems. They just wanted to feed external set points directly to the drives. So we need to be able to achieve that as well. And due to sizing, we had to incorporate not just Beckhoff drives, but different drive vendors as well. So we needed an open platform that would let us do that. And lastly, we need some high-precision measurement terminals. We have some of these out in the tech cave, if you're interested in going and have a look at those. They're the Beckhoff ELM series, so they are high-precision, well, we refer to as high-precision measurement. So we needed to achieve better than 20 kilohertz sample rates. We also had standard digital, relay, and analog signals as well. So it's this combination of safety, motion, and measurement that needed to be achieved in this one system, yeah? Because the customer didn't want to have massive amounts of different networks all running back to the same PC. Yeah. And obviously, we've noticed we've just had it introduced to you, the huddles idea. There is a huddle tomorrow afternoon on industrial protocols. I know what the answer is. Yeah. So I'll be in that one, heading one team up. I don't know who is going to challenge me with this one, but for the projects that we were looking at, we chose EtherCAT. Okay. Through the next few slides, I'm going to talk to you about why we chose EtherCAT specifically, some of the benefits that it brings, but also some things you have to be aware of when you're actually using it, because there's an awful lot of really big plus points that are brought with EtherCAT, but you have to be aware of what it's actually doing to understand how to set up these big networks. So, to lead on this conversation, and the first point, I went to where everyone goes today with engineering. I went to ChatGPT, and I asked it, is EtherCAT awesome? And it came back and said, yes. Yeah? It gave me a load of other stuff, but that's the most important thing there. Okay? So it's officially approved by ChatGPT. If anyone's questioning it. So, has anyone here actually used EtherCAT before? Quick show of hands? That's quite a lot, actually. A lot more than I expect. Yes, well, you two would do. You're from Beckhoff. That's cheating. So, I'm going to talk through a couple of things that EtherCAT brings to you. One of the main benefits of EtherCAT is an improvement in bandwidth. A lot of field bus protocols in existence have different frames that they will send, especially Ethernet-based ones, have a different frame that they will send to each individual device in a network. The minimum size of an Ethernet frame is about 84 bytes. Therefore, you have a lot of overhead when you're trying to send a byte of data. Yeah, that's 84 bytes. Just to send 1 byte of data. Whereas with EtherCAT, a single Ethernet frame is built up of multiple EtherCAT datagrams inside that Ethernet frame. So we compact all of that information down into a single frame that then cycles through the entire network. Okay? For a black channel, we can also include safety in this. So you can include what's referred to as FSOE, or fail-safe over EtherCAT communication, which allows us to push both normal sort of PLC, motion, and measurement data alongside safety data. Okay? And that sounds brilliant. You're sort of there going, brilliant. They've got this massive field bus with lots of bandwidth, but there are a couple of things you need to be aware of when you do this. Okay? Building a big EtherCAT network, which in principle is only limited to 65,000 devices, yeah, is a problem. Because once you get to that sort of size, you're talking a lot of data, yeah, that needs to then be broken up into different frames in order to not overload your networks. Okay, so 65,000 devices guarantees going to be a lot of data. Now, with a lot of machines, EtherCAT has absolutely no issue with this, but when you want to cycle at different rates, you then break up into different frames. Okay, and the other thing with EtherCAT, when it does this, is it will combine all of these datagrams and give you single point error diagnostics. Okay, which means you get the error diagnostics for everything on that network in one value, which isn't particularly useful when you don't know which thing then breaks. Okay, so the way to get around that is to divide your network up into what we refer to as sync units, which allows you to say, I want to put all my drives onto one sync unit, all my I/O onto another sync unit, and we get diagnostics specific to those pieces of equipment. Okay, and the downside of that is as you add more stuff to this datagram, the longer the Ethernet frame gets, and you can only push electrons down a cable so fast, the longer the communication time gets. Okay? And that can be problematic. The benefit of EtherCAT is that we can break up into multiple networks. Yeah, so we have headers and bus couplers that allow us to have single masters running multiple EtherCAT networks and synchronize them together. Okay, we'll come back to that synchronization in a moment. So, if anyone's not seen this before, this is the standard EtherCAT image that will get presented to you. EtherCAT is what's referred to as process on the fly. That frame that I talked about, once it's built up, will travel through every single device in your network. Yeah? The benefits of that is it's incredibly fast. There's no store and forward. There's no software stack delays in the system. There's a microcontroller in every single device that will then pull the data it needs from the frame and then replace it with the data it wants to go back to the master. Okay? That's incredibly powerful, because it means all of these devices in this network are then connected together by a frame that moves through the entire network. But you can imagine, as with the last one, the more of these devices you add, the longer your network gets, the longer your frame time gets to propagate through that network. Okay, so if you have a fast cycle rate, you're trying to achieve a millisecond cycle time, and you want to put 1,000 devices on it, you're going to be using a significant portion of your processing time just running the network. Okay? There are ways around that. We can break it up and have multiple networks, and again, we'll come back to that in a second. Cool. EtherCAT is also automatic network detection. Hopefully this is going to run. Oh, there we go. So on startup, EtherCAT will, inside each device, will then recognize the network and open up the ports, allowing it to then, allowing the frame to propagate through. Benefit of that, you don't have a lot of complex network setup. Yeah, so it doesn't matter how many devices you've got in your network, it will auto-detect and bring them all back to your EtherCAT master for you. You don't have to sit there and give IP addresses and identities to every single device in that system. Yeah. Downside of that is there's no real topology. EtherCAT doesn't really care whether you use star, drop line, line, or anything. That frame will go through every single one of these devices, every single cycle. Okay, so if someone comes along and unplugs something and plugs it in somewhere else, you can have a problem because that logical addressing of the frame then changes. Okay, if you need the ability to do that, there's a system called Hot Connect, which is part of EtherCAT, which allows it to use identity header and allows you then to move these devices around your network. But it's something you have to think about ahead of time. Yeah, it's not like other Ethernet-based systems where you can plug them in everywhere because of the network IP addressing. And probably one of the most powerful things about EtherCAT is the distributed clock system, or DC system. This allows us to synchronize devices in an EtherCAT network to incredibly high precisions. Yeah, we've actually measured in applications down to less than 100 nanoseconds between devices doing their input measuring and their output setting. Yeah, and that's one of the things that makes it suitable for this measurement field bus. Okay, we can be incredibly, incredibly precise with the timestamp of the data we're getting from our analog devices. Okay, there is a period at the start of EtherCAT setup where it will initialize and bring all these devices into synchronization, and once they're in sync, you then have a datagram that goes out with the Ethernet frame that keeps them synchronous to each other the whole way through. And the way that's done is we have a device in the network that effectively becomes what we refer to as the reference clock or the master clock for the system. Okay, it provides the time reference for the entire system on the basis that the one in the IPC is going to be rubbish, which it typically is. Yeah. The benefit of that is that we can replace this reference clock with pretty much any reference system we like. Yeah. At the moment, and this system here, you can see I've got a bit of hardware with me today. It's just a terminal that's in this system, so it's an EtherCAT device. But that could easily be a digital input from another system that's a very high precision input. It could be an IEEE 1588 Grandmaster reference coming in, which means you can go from just synchronizing your local systems to synchronizing systems across sites, across countries, if you want to. We have some customers that are doing it across the UK. So there's a site in Scotland, near Glasgow, that's actually running in sync with a system down in Cambridge as a test. And I don't know how they measure this, but they've got proof, effectively, that the digital outputs are all set the way they want them to within a microsecond of each other, which is pretty good. So the thing to be careful about with this is, while that all sounds brilliant, that reference clock decides what devices in your network are going to be in this DC network. So if you didn't choose this one, for example, and made this S2 here your reference clock, none of the previous devices would be in it. So specifying your reference clock in EtherCAT is important, okay? Because you can unwittingly turn a lot of terminals or a lot of EtherCAT devices out of that system by poor choice of placement of your reference clock, okay? Cool. So that all sounds wonderful. We have an EtherCAT system. It may surprise you to notice, given that I work for Beckhoff, the controller we chose for this project was a TwinCAT Beckhoff PLC. This gives us a real-time PLC, also with a OS that sits atop that, so Windows 10 in this particular case, but BSD, and there will be a Linux operating system coming in the future, which makes it a big open platform now for us. The IPCs themselves, you can see I've got a small one on demonstration here on my stand. We have the ability to run the TwinCAT PLC operating system, so it's a real-time operating system that we use for our automation customers. It runs EtherCAT masters. It can also run a number of other masters, which I'll come back to in a second. But the main benefit about this is it gives us that real-time deterministic PLC logic, and it gives us a Windows OS where we can run executables and other operations, so databases, that sort of stuff. It's capable of running multiple EtherCAT masters. And coming back to that topic of synchronization, it is not just the case that we can synchronize an EtherCAT network, we can synchronize EtherCAT networks on the same PC to each other. Okay, so you're not just limited to trying to shove everything onto a single EtherCAT network. If we want to break up networks, we can use one port for EtherCAT, the second port for EtherCAT, and then synchronize those internally inside the PC, okay, and achieve those results. We have devices, or there are devices in the world that aren't all that are Beckhoff and third-party companies as well, that have EtherCAT slave interfaces on their controllers. What that means is you can have a high-level PC and then divide it up into a load of PLC units that are then EtherCAT slaves to that high-level PC. So your high-level PC gives you that grand reference clock, and then it filters down through all the other PCs, and they then take their time reference from that one. Yeah, if anyone's ever seen the kinetic rain demonstration at Shanghai Airport, that piece of artwork where all the golden drops move up and down in synchronization, that's all done through that process. It's one grand PC that runs the artist's impression of what should happen, and then a load of smaller PC devices that are running the individual chains of those droplets. So TwinCAT is a modular platform. It can allow us to run multiple things internally. We have obviously a PLC, we have integrations for C++ and Simulink, and all of that allows us to then run automation and talk to any field bus that we care to using this thing called the automation device driver. And that's how we achieved the network the customer was after. We had an EtherCAT master, a Profinet master, and an Ethernet IP network. We had a lot of different devices talking on a lot of different networks, and we needed a controller that could do all of those networks in one go. Yeah? So we took EtherCAT for the Beckhoff hardware, even the NI 9145 that you can see in front of me here. And then we had some drives that were Profinet drives and some Ethernet IP devices that I can't remember what they exactly were off the top of my head anymore. But yes, so TwinCAT was able to run all of that for us. So then what did we do with that? We pushed it all to LabVIEW. Okay, the customer didn't really have that much interest in learning TwinCAT programming. You can do it in some graphical languages like continuous function chart, but what they wanted really was to get it all into LabVIEW as quickly as possible and do all of the operation in there. So all the TwinCAT system did was provide a method of controlling your networks, a method of setting it all up, and then allowed them to push that data via a system we call ADS into LabVIEW. Okay. Again, surprisingly for this demonstration, I chose to use the Beckhoff product, which is a VI library called TF3710 that allows us to communicate with Beckhoff IPCs over this ADS system. Now, ADS is a really nice real-time to non-real-time communication protocol. It allows us to string Beckhoff PCs over large networks of IT infrastructure networks and then pass data back over ADS to databases, HMIs, etc. In this case, we chose LabVIEW because then we could do the analytics piece. What we ended up doing in reality was not running LabVIEW on a separate computer. We actually ended up running it on the Beckhoff IPC. We realized we had more than enough overhead for them to deploy their LabVIEW application as an executable onto the Windows system running on our Beckhoff IPC. Okay? Which made life a lot easier for us. It meant less cost. We didn't have to worry about too much about networks. And they could then control that using their own internal processes. So, this is the bit where we'll see if this demonstration is going to work or if I'm going to have to fall back on the emergency videos that I made last night. I did post something on LinkedIn saying that I had my presentation ready. This is absolutely not a photo I took in the hotel at 11 p.m. last night of the desk rig. But I'm going to try, and hopefully, it's going to let me do this. Have I got a connection? No, I've annoyed it. Let's see. This is always the way. As soon as you try and do something in front of people, it doesn't work. Hmm? That's it. I know how close I am to just trying the trusty switch off and switch back on again. That's what I'm going to do. So, what I've got here, I don't know if it's actually available currently, no, is, if this is going to work, a set of VIs that I made, demonstration VIs. They're all, we wrote them into a GitHub repository, so anyone can come and try this. I will keep this kit available for the 3 days, so if anyone wants to come and just play with it, that's absolutely fine. But effectively what we have is a demonstration of 3 methods of actually controlling this. So I'll fall back on the videos for now, and then if this works, I'll come back to the live demo. So we have a poll reading. So what this is over ADS, you can just request information. Now this can be from anywhere. So the ADS protocol we can use from anywhere on the planet. As long as you have a valid ADS connection to the system, your LabVIEW application can basically be anywhere. Yeah, we have customers that do this over VPN, E1 tunnels, cloud-based systems, etc. Is this going to play? There we go. So, by a poll reading, we can read very basic signals. This is just a potentiometer that's on the rig there, obviously just being pushed into a waveform chart. The limitation with poll reading is that it's very much a server-client based protocol. So it's I want this bit of information, here it is, thank you very much, error check it. That gives it a speed limit, effectively. You wouldn't want to do this for analog signals. Okay, your maximum you're probably going to get out of that is 500 hertz to a kilohertz of data. Now, TwinCAT will compact all that, so you'll get a lot of information in that, but it does slow down your processes. So, to deal with that, we have an option for what we refer to as event-based reading, which is what's going on here. So what's actually happening, if I can start both videos at the same time, if it will allow me the pleasure, hold on, is we have the motor rotating. Where's my mouse gone? There it is. And as the motor rotates, there's a sensor on the system that is a counter module, and that is then being updated by this system of event-driven reading. So what that basically does is the LabVIEW interface allows you to put a notification, either cyclic or on change, on the variable you're interested in reading. Okay, and it will just push data to your client that you can then bring in. So this, we have demonstrations of this achieving 5, 10, 15 kilohertz cycle rates. We have one customer that's pushing 2,000 long reels, so 64-bit data every millisecond out of a Beckhoff PC via that system, which is actually quite a lot. It's a lot more than they need as well, but they won't reduce it because they like the fact that it sends that much. Okay. Sweet. Thank you very much. I'm going to have another bash at the demo. Otherwise, it's going to typically fail miserably. There we go. We're going to come back. Let's see if this is going to work. No, this is really tricky to see from this angle. Ah, no. Ah, yeah. Huh? It would happen. It was the annoying thing is, when we were doing the demonstration, the test at 8 o'clock this morning, it worked perfectly. Now I've unplugged something, and now it's having a tantrum. But I promise you can use ADS all over the planet over any network you like. Yeah? This one Ethernet cable, that's what's letting me down here. Give it another bash. Yes, so what I will do if I show you what it looks like in TwinCAT. Yeah, yep. Well, maybe, who knows? It was working earlier, now it's not working, so. Yeah, so basically the TwinCAT system I'll show you now, so this is obviously TwinCAT Visual Studio-based engineering environment. All it's doing is running this EtherCAT network, basically. Well, actually, technically two separate networks. I have one network coming into this EK coupler here with some safety on it, which should be working. And I have another one running this bank of I/O over here. There we are. So in TwinCAT, all I actually have, come down here, is my EtherCAT network. In here, you'll see the first bank of I/O with our devices in there, the NI chassis, and then the second bank of I/O, which is just the two couplers on this system. So we have a servo drive in there, which if the demonstration was working would spin, I promise. And then we have a second EtherCAT network here. And all that's happening is LabVIEW is pulling the data directly from this I/O network. Okay, so there's nothing up here secret going on in the PLC. I can prove it. That's the code that's in there. Yep. There's nothing actually going on. And that's the network. Does that make sense? Brilliant. Right. I will have this working when you all go outside. I don't know why that stopped, but there we go. So that's my time. I think I've got 3 minutes left before I get carted off stage. Is there any questions on that so far?
I'm really curious. What was the artwork you were referencing? Sounds cool. The artwork with the synchronization.
Yeah. The kinetic rain in Shanghai Airport. Have you ever seen that? Hold on. I'll Shanghai Airport. Let's see if I can. Yeah.
Oh, cool.
Let's see if I can get one come back.
And then a more technical one. Where are you doing the translation from Ethernet to Profinet? You mentioned that there was.
Sorry?
I think you said you were doing a combination of Profinet and Ethernet in one of the examples you showed?
Yes.
So are those networks just talking both to LabVIEW that's relaying data between them? Or
no, so both those networks are talking to TwinCAT. TwinCAT gathers all the data together in one place and offers it up to LabVIEW. So TwinCAT is a centralization of all of those systems because it gives us the ability to use all of them without having to use multiple different vendor systems, basically, in our application. It simplified the control logic a lot. We didn't have to use things like HMS converters, which you can use to translate between the fieldbus protocols. And it allowed us to synchronize everything back up in the IPC itself and then pass everything up to LabVIEW. So we actually, there's a lot more work went on in the actual application to make sure that the Profinet data matched up the EtherCAT data, and then we could bounce it back. But Profinet, standard Profinet RT doesn't have that synchronization piece that EtherCAT has, which is one of the things that makes EtherCAT better in those scenarios because it has that built in. The closest thing that Profinet has to EtherCAT is Profinet IRT, which Siemens have actually stopped developing effectively now. Yeah? Anything else? Nope.
Thank you for the presentation. My question is, how would you compare the Beckhoff ADS to OPC UA, which is also like non-real-time communication with PLCs?
I mean, the thing about ADS is Beckhoff specific.
Okay.
Yeah.
And then
so it is an open standard, so you can use ADS and develop your own servers and clients for other machine vendors, PCs. We have customers that do that. The thing about OPC UA is that all the PLC vendors have signed up to OPC UA and they all implement it and it's all the same, right? So that's the thing that OPC gives you. The benefit of Beckhoff, I have to say this because my boss is over there, or my boss's boss. Are you my boss's boss or my boss's boss's boss? I forget. But basically the benefits of it, of the sort of Beckhoff system is that it can use both at the same time, and we can send ADS securely over OPC UA if we want to as well. So the ADS connection can be made secure as well as just being an open TCP protocol.
Okay, thank you.
So maybe we could watch it later, but a short question. What is the exact role of the so-called safety module, which I also spotted somewhere in your demo?
Yep, so the safety module, this is just how we develop the safety projects in TwinCAT. This bit here you're referring to. So it's doing nothing more complicated than running an e-stop. So it's a continuous function chart integration that we use to build up safety networks. All it's doing is running the functional safety terminals on this device, which I can show you when I get it working again. But yes, that's it. So and all that gets downloaded into a controller. So this first yellow terminal here is actually the safety controller that sits inside the EtherCAT network. Now that can sit anywhere inside the EtherCAT network. That's the other advantage of TwinSafe and failsafe over EtherCAT technologies. The actual safety logic, the controller and the safety terminals can just be anywhere in your network. So it's been quite useful in automation because it's moved us away from having a cabinet that's just safety and running a lot of wiring back to that cabinet to pushing islands of I/O like this, like these two here, with safety terminals integrated much closer to the machine where the actual contacts, relays, whatever it is that they need to be near are. Yeah? You good?
Thank you very much. If there are any more questions, we'll follow it on Discord.
Would have been more if it would work.
If it works.
Cool.
Thank you.
Thank you.